Okay, so this is a short chapter. It's on periodic trends. That's what that title essentially means. Okay, and I want you to understand, guys, what a single electron is experiencing at any given point in time. And there's a lot going on. Okay? Because electrons are moving at all, they of course have kinetic energy, the energy of motion and movement. They also are experiencing, if you look down here, some potential energy. They are experiencing repulsion between themselves. Now, why would two electrons repel each other? Yeah, they're like charges. They're both negative. Like charges repel. But it's this potential energy in the middle. This is probably the most important one. This is the one we're going to talk about a lot today. And it has a fancy name. It's called the effective nuclear charge. Okay? This is the variable that it stands for, or it stands for it. Okay? You have my permission. If on a test you need to use the term effective nuclear charge, you have my permission to just write that variable, ZF, Z effective. And that effective nuclear charge, guys, is a force of attraction between the nucleus and an electron. Now, why would an electron be attracted to the nucleus? Yeah, they're oppositely charged. Think about what's in the nucleus. Protons. Okay? And for those of you that are more physics-minded, think about the fact that a proton is magnitudes larger in size compared to an electron. So, what do you guys think? I mean, just use your common sense. Do you think that this is a very strong attraction, weak attraction? What do you think? Very strong. I mean, electrons are teeny tiny. Think of the nucleus, those protons in the nucleus, as like this gigantic magnet. Okay? Now, again, let's think a little physics here. If this force of attraction is so strong, which it is, how come electrons don't just collapse and do what they feel like doing and go towards the nucleus? I mean, they're so attracted to the nucleus. Why don't they just go there? What's preventing them? There's a couple of things going on. I see you doing that. What does this mean?
When things are moving, or when things have a velocity, they can create these circular motions even when there's a force pulling towards the center of the circle.
Okay, exactly. But also, think about the fact, guys, that if electrons collapsed down on themselves towards the nucleus, wouldn't all these electrons then be getting closer to each other? And they don't like that. Okay? There's a force of repulsion. So there's a number of things going on here. Okay? But this is where we're going to focus today. Okay? And here's the deal, guys. If you can understand the trend on the periodic table for effective nuclear charge, you can understand all periodic trends. Because, ladies and gentlemen, all trends, and there's a lot of them, like ionization energy, electronegativity, atomic radius, ionic radius, all of these trends are a factor of the effective nuclear charge. If you can understand this, you can understand all of them. All right? Let's talk about the two directions. Okay, let's talk up and down. let's say we are comparing the element lithium and cesium. Lithium and cesium, they're in the same group, same family. All right, this says as we move down a column, the effective nuclear charge gets weaker. Now you guys tell me, every time I move down a row on the periodic table, what is that like in terms of atomic structure? What am I gaining one more of every time I move down? An energy level. Okay. Well, if I am progressively moving another energy level further away from the nucleus, I am getting physically farther away from the source of that attractive pull. So if I'm an outside electron, if I'm a valence electron and I'm getting further and further away from the nucleus, I will be experiencing a weaker and weaker and weaker force of attraction. Okay? So when you're talking about up and down, you are talking about different number of energy levels. Okay? Elements that have fewer energy levels, their valence electrons are closer to the nucleus, so they will experience a stronger effective nuclear charge. Let's talk left to right. Let's say we're comparing sodium and chlorine. Now, do you all agree that sodium and chlorine are on the same row? Yes? Well, what does that really mean in terms of atomic structure? Their valence electrons are on the same energy level. Okay. So based on that, you might say, well, shouldn't they have the same effective nuclear charge? No, they don't, because although, yes, the valence electrons are on the same energy level, every time I move over one box to the right, what am I gaining one more of? Okay, yes, I am gaining one more valence electrons, but even more important than that, I'm gaining one more proton. Okay? And guys, remember, protons are the source of that effective nuclear charge. So, although sodium and chlorine have valence electrons on the same energy level, chlorine has more protons, which means it has a stronger effective nuclear charge. If those two directions, those concepts, if that makes sense to you, the rest of today will be very easy. Okay? Because those concepts, guys, explain just about everything. Okay, as I said, guys, there's multiple periodic trends. Atomic radius, ionic radius, ionization energy, electronegativity, electron affinity. There's a lot of them. The AP exam has decided that this is the most important one. I don't know why, but we're just going to go with what they say. So let's make sure we remember what this term means. Ionization energy. The energy required to remove an electron. Okay, that's not the full definition, but that's the important part here. Okay, and let's just make sure we've got this. If it is very, very difficult to remove an electron, will the ionization energy be high or low? High. If it's very easy to remove an electron, it'll have a low ionization energy. Okay? Well, for the moment, don't cross this out in your notes or anything, but for the moment, let's ignore the word first there. We'll come back and I'll explain why that word first is there, but we're going to ignore it for the moment. let's talk about up and down. Okay? Now guys, on our next test, which is coming up, by the way, it's on Monday. I haven't even updated the board yet. Okay? Here's what you will be presented with on free response. You will be given statements, okay? Not questions, statements that are true, and your job is to explain why the statement is true. For example, we're talking up and down. Let's say the statement says this: cesium has a lower ionization energy than lithium. Period. Your job is to explain why that's true. Okay? So let's talk about it. It's for the same reasons. Okay? You guys help me fill in the blanks here. Cesium contains more filled what? Energy levels. Cesium contains more filled energy levels and thus experiences a blank effective nuclear charge. Weaker or stronger?
Weaker.
Weaker. Period. Cesium versus lithium. Cesium contains more filled energy levels and thus experiences a weaker effective nuclear charge. Okay. How about left to right? You come across a statement on the test that says, let's say we're comparing aluminum to chlorine. Okay? Aluminum to chlorine. And the statement says chlorine has a higher ionization energy. And your job is to explain why chlorine has a higher ionization energy than aluminum. Okay? So let's fill in the blanks again. Although aluminum and chlorine possess the same number of what? What do they have in common? Energy levels. Although aluminum and chlorine possess the same number of energy levels, chlorine contains more blanks. Protons, and thus experiences a blank effective nuclear charge. Stronger. There you go. Although aluminum and chlorine possess the same number of energy levels, chlorine has more protons and thus experiences a stronger effective nuclear charge. Okay? Now, let me tell you something about these test questions, which you'll see on my test, you'll see on the real AP exam. We are different than AP Bio, for example. AP Bio is a test written where they have actual essays, okay? We don't have essays on ours. We have these sometimes short answer questions, and guys, there's actually a maximum for how much you can write. On questions like this, where you have to explain something, there is a 2-sentence maximum. If you write more than 2 sentences, it will not be read. So just stop writing. That means you have to get your point across in a very succinct, concise way, which is easier said than done. And it can't be run-on sentences, people. Comma, and, semicolon. No, 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 no. Okay? We're talking 2 normal length sentences. Okay. So guys, I'm not even going to go over this because we've already gone over this, okay? This is the written out explanation of the up-down direction. Here is the written out explanation for left to right. But we've already talked about it, so I'm moving on. Okay, now, bless you. I said a couple of slides back, just for the moment, let's ignore that word first. Well, now let's talk about it. Because there is something called a first ionization energy. There is also a second. There's a third, a fourth, a fifth. Let's talk about what that means. First ionization means the energy required to remove one electron. Second, and I want to make sure this is very, very clear because this is kind of a misconception. Second ionization energy, guys, means one electron has already been taken. How much energy does it take to remove a second one? Many people think, mistakenly, that this is the amount of energy it takes to pull off two at once. And that's not what's happening here. Okay? One has already been taken. How much energy is required to remove a second? Okay? And if we're talking third ionization, how much energy does it take to remove a third, a fourth, etc.? Okay? Now, this is something, and I don't get to say this very often in this class. This relationship here is true for every single element, no matter what, no matter where it is, no exceptions. I don't get to say that very often in here. This says whatever element we're talking about, doesn't matter where it is, whatever the first ionization energy is, whatever that number is, to remove a second electron will always require more energy than it did to take the first. And to remove a third will always take more energy than was required to remove the second. Okay? It does not matter what element it is, that will always be true. For example, look at this data here. This is data for magnesium. Okay? And we're going to talk about two different things that we can see here. You might have a question, like a free response question, that gives you data like this. And it might say, explain this trend, or explain this data. And that's very vague, but let me tell you what they're trying to say to you. The first thing they want you to explain is, why are these energies progressively getting larger? Okay, well, let's talk about that. If I remove one electron from magnesium, have I changed the number of protons? No. If I remove a second electron, have I changed the number of protons? If I remove a third? No. The amount of protons is staying the same. The amount of electrons is decreasing. And guys, I want you to think about electrons and protons being kind of like in a tug of war with one another. Okay? Proton team is over on this side, the electron team is on this side. And I keep removing members from the electron team. Who do you think is going to be winning this tug of war? The protons. Well, when I say protons are winning the tug of war, what I'm really saying is the effective nuclear charge is getting stronger and stronger and stronger. Okay? I'm going to give you an analogy and then I'm going to explain it to you you know, on how you would say it on a test. All right, and this is a little depressing, this analogy, but I think it works. Okay. Could you tell me, please, look at where carbon is on your periodic table. Carbon. How many valence electrons does carbon have? 4. Okay. I want you to think of the nucleus of carbon as like a mother, and those valence electrons are her children. She has 4 children. Okay? And one of those children is abducted. Okay, that's like my worst fear in life. Okay? Okay, so one of her children is abducted. Don't you think that she's going to hold on to her 3 remaining children a little bit tighter than before? And God forbid, if a second child is abducted, and at this point we're calling Child Protective Services, right? Am I right? But let's say, God forbid, a second child is abducted, those 2 remaining children, she's like never letting them out of her sight. Okay? She is going to hold on to them so tightly. Terrible analogy, I agree. But it works, right? Yeah. Okay. So, let's say you're answering a test question. People, you got to be really careful what you write on these test answers. You can't say, well, it's increasing because the mom is, you know, she wants to hold on to her kids. No, you can't say that. Okay? Here's what you would say. Are you ready? Tell me one more time. Is the number of protons changing? No. But the number of electrons is decreasing. We agree? Okay. The ionization energies are steadily increasing because the proton to electron ratio, ooh, fancy. The proton to electron ratio is increasing. Okay. Let's keep this whole fill in the blank thing, which causes the effective nuclear charge to steadily blank. Increase. Okay? I feel like you guys really like this whole fill in the blank thing. Don't you wish the test could be just all fill in the blank, matching? No. Okay? So, ionization energy steadily increase because the proton to electron ratio is increasing, which causes the effective nuclear charge to also increase. Now, there's something else I want you to notice about this data. Increase, but from here to here, guys, it's not just an increase. It's a big increase. Look at where magnesium is located on your periodic table. Anybody want to hazard a guess as to why there's such a big jump when we try to take that 3rd electron? Jack, what do you think? Okay. So you're saying taking that 3rd electron is taking it from a lower energy level? Okay. Definitely correct. Let's also think about what types of electrons we're looking at here. These first 2 electrons that were removed, what type of electrons were they? Valence. What about this 3rd one? It's a core electron. Okay? But I'm going to put these 2 things together. I'm going to put the valence versus core thing together with what Jack said, because they're both important. You might see a question that says, explain why there is such a large increase from here to here. Much more energy is required to remove a core electron, and not just a core electron from a filled energy level. That's big time. Okay. It takes much more energy to remove a core electron than a valence electron. And not just any core electron, but a core electron from a filled energy level. Okay? So what I'm going to ask you to do, and I don't do this a lot, but I'm going to ask you to do it today, is I want you to look at this and explain this to somebody sitting near you. Because if you can explain something back, that means that you truly get it. Okay? So here's what I want you to do. All right? I want you to talk about two things. Number one, why are we seeing these energies progressively getting larger and larger? That's the first thing I want you to explain to somebody. And then maybe the other person, explain in AP Chem terms, don't talk about mothers and children, okay? Why do we see such a big jump? Take 2 minutes, go. Okay, so here's something else that might come up. Okay, let's see. Let's do a little true-false. All right, true or false? As you move from left to right across the periodic table, ionization energy increases. True or false?
True. True.
You're correct. Okay, well, I'm going to make up some numbers here. All right, now, yes, I'm just making them up, but they are representative of true things. So I'm just making this up. Let's say this has an first ionization energy of 300 joules, and this one has a first ionization energy of that. Well, wait a second. Wait just a darn second. Didn't we just say moving from left to right, ionization energy increases? Isn't that what we just said? So I've been lying to you this whole time? No. There are exceptions to the rule, okay? Guys, this is like the essence of AP Chem. Here's a big rule, da-da-da-da. Oh, but wait, there's a whole bunch of exceptions, okay? That's like the essence of higher level chem. You know, was all of Chem 1 a total lie? No. It just wasn't a totally complete picture. So, I want you to look at this, all right? Let's compare beryllium to boron. Beryllium, group 2, has 2 valence electrons. Boron has 3. I'm going to circle the electron that would be removed. And guys, pictures speak 1,000 words. This is going against the trend that we usually know, but forget about using like technical AP Chem terms. Can you just kind of look at that picture and maybe give some kind of explanation? Why do you think it might be a little bit easier to take this guy away than this guy? Forget about using technical words. Like, just speak from the heart. Speak from the heart, Kevin. Tell us.
Well, the one on the 2p energy level is all alone, and it's a lot easier to remove someone who's all alone than someone who has a friend.
Yeah. Yeah. It's easier to take someone away when they're not tied to anybody else. This guy is linked up here. Don't you think that his little partner here is going to be upset? Okay, now, the essence of that is right, but I cannot stress enough, how you can't use these kinds of explanations on tests. Okay? Are you ready for the technical explanation? Okay, well, first of all, guys, would you agree that this 2s sublevel, would you agree that it is full before I take that electron away? It's filled, right? How would, before I take this one away, how would you describe this sublevel? It's not full. It's not even half full. It's, how about this? You don't have to be so specific, 1/6 full. How about it's partially filled? How about that? Okay? Don't say 1/6 filled, that's silly. All right? I know it's not wrong, but here's what you would say, ladies and gentlemen. Are you ready for the technical jargon? Less energy is required. Less energy is required to remove an electron from a partially filled sublevel than from a filled sublevel. I'll say it again. Less energy is required to remove an electron from a partially filled sublevel than from a filled sublevel. And if this were me, ladies and gentlemen, I would draw this out. Okay? Remember, you are still working against that 2-sentence maximum. Drawing a picture like this does not cut into your word count. Okay? I would, if this was me answering this question, I would draw this orbital notation out. So this exception to the general left to right ionization rule happens from 2 to 13, beryllium to boron. What other two elements might we see this between? Yes. Magnesium to aluminum. Okay. You would see it from calcium to gallium too, but there's all those transition metals in the middle. It gets a little murkier. Okay. Let's look at another place that's an exception to the rule. Okay, and this time I'm going to use the element nitrogen. Nitrogen has how many valence electrons, ladies and gentlemen? 5, okay. Let's see what you remember. Whose rule explains why I just drew these arrows up, down like that? Pauli exclusion, okay. Whose rule explains why I'm drawing the arrows up, up, up? Hund's rule, very good. Okay, oxygen just next door has 6 valence electrons. Okay. This is another exception to the rule. I'm going to make up some numbers again. Maybe nitrogen has an ionization energy of 475 joules. Maybe oxygen has a first ionization energy of 461. That's a violation, or not a violation, it's an exception to the rule. Again, look at the picture I've drawn here. Before this electron is taken away, guys, how would you describe this sublevel? Half filled. How about before this one's taken away, how would you describe it? Don't say 4/6. Oh, fine. I walked into that one, didn't I? It's 2/3. Partially filled is the answer. Smarty pants. Okay. Anybody want to hazard a guess as to why this number is a little lower than this one? Now, think about what we wrote for this one. It's almost the same exact explanation with just one word difference. Less energy is required to remove an electron from a partially filled sublevel than from a half-filled sublevel. The take-home message here is, guys, filled sublevels are very energetically stable. It takes a lot of energy to break up a filled sublevel. Half-filled sublevels are the next in order of difficulty to break up. Partially filled, not as much. Now, you guys are smart. You guys know you're not going to write explanations on the test that involve mothers and children, and this guy's got a partner and he doesn't want to lose his buddy. I know you're not going to write that, but there's things that you will be tempted to say, like, nitrogen doesn't want to lose an electron. Elements don't have feelings, okay? You're going to be tempted to write things like that. Don't do it. Okay? Okay. I'm actually going to skip over that. Let's get to this. Because this is something that you have likely not done. Okay. So here's the deal, guys. This is how most, not most, I would say some ionization energy questions will look like. Sometimes on free response, there'll be question or statements like what we were just talking about. Here's a statement and you have to explain why it's true. This is another way you could be asked a question about ionization energies. You will be given graphs that look like this. Okay, they're called PES graphs, Photoelectron Spectroscopy graphs. Do not be intimidated. Okay. First of all, this term, binding energy, you can think of that as being basically the same thing as ionization energy. Okay. This is how much energy is required to remove these electrons. Okay? And you're going to see peaks. Okay? Some are short, some are taller. We'll talk about why they are different heights. Okay? So, here's the first part of this. Remember, anywhere that it says binding energy, you can think of that as, if that makes you uncomfortable, swap out the word binding and put ionization energy in. Each peak, ladies and gentlemen, represents one sublevel. Okay? So, for example, let me change color here. On this graph, this first peak right here, when we write electron configurations, what's the very first thing we always write? How does any electron configuration start? 1s2. Okay, so this peak right here, that is the 1s sublevel. And how many electrons would be in there? 2. Okay. What's the next thing you write in an electron configuration? 1s2, then what comes next? 2s2. This peak, that's 2s. What comes after 2s? 2p. Okay, great. Each peak represents a sublevel. And I'll come back to this in just a second. I'll explain that in just a second. Okay? And I should have done this before. I'll rewrite it. Okay, this is 1s. 2s, this is 2p. Each peak represents a sublevel, and each peak height, how tall that peak is, corresponds to how many electrons are in there. Do you all notice that peaks A and B are the exact same size? You know why that is? They both have 2 electrons in them. Okay. Look at what element this is for. This is for neon. Look at where neon is on your periodic table. There's 2 electrons in there, 2 electrons in there. How many electrons does neon have in 2p? 6. That peak, C, it's probably not perfect, is 6 times higher. Not 6, sorry. 3 times higher than the other peaks. It should be. This peak contains 2 electrons. This one has 6. It should be 3 times higher. Okay? Now, why, and think about that term, effective nuclear charge. Why are the 2 electrons in 1s, why do they have such a higher binding energy, ionization energy, whatever you want to call it? Why do they have such a greater ionization energy than, say, the 2 electrons over here? Yeah, what do you think, Trent?
Because they're core electrons.
Okay, that's true. They are core electrons. Okay, that's definitely an issue here. What else? Yeah, Nafisa. Okay, there's a lot going on here. Yeah, it's a fully filled sublevel. What else? Okay. It's on the first energy level, guys. Does that mean that it's close to the nucleus or far away? Very close. If you're close to the source of that magnet, do you think it's easy to take those electrons away? No, no. Okay? These 2 electrons in 1s have a very high ionization energy. And guys, I realize this is a little weird that you're reading the graph kind of backwards. Okay? Focus on the numbers. This has an ionization energy of like 875, whereas this has an ionization energy of 50. It's much more difficult to take electrons from 1s because these 2 electrons are experiencing such a strong effective nuclear charge. Okay, now, let's be clear about something, because these graphs are kind of, they're sort of hiding something. I want to talk about why I say this, and then we'll do some practice. This graph is telling me, in fact, let's use this one. Okay, so this is neon. These are the 2 electrons in 2s, and this graph is telling me that both of those electrons have the same ionization energy. That's like saying lithium and beryllium, because that's 2s. Do you all agree? Right in there. That's like saying these 2 have the same ionization energy. Do they have the exact same? No, they don't. This graph makes it look like they do. They're close to each other, but you guys tell me, which element, lithium or beryllium, which one technically would have the slightly higher ionization energy? Beryllium, yeah. Taking the second electron out of 2s would actually require just a little bit more energy. Okay, but we're gonna just focus on these peaks. Now let's look at some kinds of questions that you might be asked. Same exact graph. Okay, so let's answer these together. What is the relationship between binding energy and effective nuclear charge? So I'll set the scene for you. if an electron, or maybe even two electrons within the same sublevel, if they are experiencing a very strong effective nuclear charge, large effective nuclear charge, will my number for the binding energy, the ionization energy, will it also be large or very, very low? Which one? Strong effective nuclear charge? Very large ionization energy, or high number for binding energy. This is a direct relationship. The stronger the effective nuclear charge, the greater the binding energy. Okay? What were these peaks again? Peak A represented electrons in which sublevel?
1s.
1s.
2s.
Okay. Why is peak A so far to the left of B and C? Let me ask it another way. Why does peak A have such a greater binding energy than B and C? It's not just because it's a core electron, there's a bigger reason. It's on which energy level, first of all? It's on the first energy level. What is it experiencing that is so much greater than B and C? A much stronger effective nuclear charge. That's why it's so far to the left. It is one whole energy level closer to the source of that magnet. Okay? Why is peak C 3 times the height of A and B? What does C represent? 2p. How many electrons in 2p for neon? 6. How many electrons are represented by peaks A and B? 2 each. Okay, great. Let's look at another practice one. Okay. Don't be thrown off by these little lines. Focus on the peaks. It says the figure above shows the photoelectron spectrum for what element? Okay, now remember, each peak represents as a sublevel, one sublevel. Read just like we do in English from left to right. What's always the first sublevel in an electron configuration? Okay. 1s. What's this one?
2s.
Okay. 2p. Do you see that it's 3 times the height? What's this guy?
3s.
Okay. Do you notice? There's lots going on here. Do you notice that this guy, and this guy are all the same height? 2 electrons, 2 electrons, 2 electrons. What's this guy? 3p. So this sublevel must be what?
4s.
4s. Now, do you notice anything funny about that last peak? It's half the height, which means how many electrons are in there?
1.
Very good. What element ends with its configuration 4s1?
Potassium.
You got it. You guys are so smart. Okay. The question says, on what energy level is the electron in the 6th peak? 1, 2, 3, 4, 5, 6. The 4th energy level. There you go. I think these graphs are kind of fun. I'm a weirdo. I know. It's okay. I'm comfortable with it. Okay? But the take-home message here is, guys, we always read them from the highest ionization energy to the lowest. And think about how electron configurations go. 1s, 1s, 2s, 2p, etc., etc., etc. Okay. Now, let me say something about this to you. I could be wrong, but I'm 99% sure your textbook does not have PES even in its, like, at all. So there won't be any PES practice problems in the problem set. What I have done, and this is totally optional, okay? I got a resource from a good friend of mine who teaches AP Chem over at Herndon. What I will put up on Blackboard, it's a set of notes that explain this again, okay, in a little bit more detail than I've gone through. And it has some practice questions with the answers on it. So I would suggest before the test, take a look at it. Okay, I'll put it up on Blackboard so that you can access that. Okay, there is another trend, which, guys, I'm going to mention just very, very briefly because it doesn't come up very often. It's a trend called Electron Affinity. Okay, and guys, Electron Affinity, if you look at the definition, is the exact opposite of ionization energy. Think about what that definition was. The energy required to remove an electron. And by the way, go back in your notes right now before we forget. When we've defined ionization energy, go back to wherever you wrote that down. The definition for ionization energy, the energy required. Ladies and gentlemen, think about that language. The energy required. What type of situation is that? Endo or exo if energy is required? Endo. What kind of energy values do we see that are endo? Are they positive or negative? Guess what? All ionization energies, no matter where, no matter what element, always positive, always endo, no matter what. The reason I'm bringing that up here, this is also an energy, and it's the opposite. It's the energy associated when you are adding an electron, and I don't want you to think, oh, well, it's the opposite, so these guys must always be exothermic. No, they're not. Okay? Some of them are, some of them are not. Can you guys think of, look on your periodic table, can you think of a family of elements? And I'm going to use a word that I don't want you to use on a test. Can you think of a family of elements that would really, really like, don't say that on a test, an element that would really like to gain one electron? It would make it really happy. Your halogens. Because gaining one electron would make it have 8 valence electrons. That's really stable. Things like your halogens will have very, very exothermic electron affinities. Okay? Meaning they welcome it. They get that electron and they're so happy about it that they release all this energy. Yay! Okay? That's a really silly way to think of it. What's an element, give me an example of an element that would really, really not like to gain an electron? Yeah. Your metals, the ones that probably want it the absolute least would be your alkali metals. Okay? Your metals will tend to have positive, meaning endothermic electron affinities. They do not want to have an electron added. Okay? Are you going to see a lot of questions on this? No. Maybe one, if any. So I'm not going to dwell on this for very long. Okay? Let's wrap this chapter up with something nice and happy. How many of you in Chem 1 learned the periodic trend for atomic radius with the snowman? Okay? Yeah. So, you have a nice snowman. In AP Chem terms, please, tell me, why does the radius of atoms, as we move down a column on the periodic table, why does the radius get larger? Don't say the snowman. We're getting increasing number of filled energy levels. Wasn't that the same exact explanation for everything else that we've talked about in this direction? Radius increases because we're getting more and more filled energy levels. And then if you're like me and you have this little gang of 8-year-old jerks in your neighborhood, I swear, they're all juvenile delinquents and they're all going to end up in jail someday. Okay? My beautiful children last winter built a magnificent snowman. Magnificent, people. And the little 8-year-old jerks on their stupid little bikes, what do? You knock it over. Jerks. Okay. And then I got all like mama bear on them, and I came outside with my baseball bat, and I'm like, get out of my yard, okay? You take your stupid little BMX bikes and you go somewhere else. Don't ruin my children's happiness. Get out. Anyway. I'll move on. Okay. Why, use AP Chem terms, please. Why from left to right does atomic radius decrease? This is a two-part answer. Although they have the same number of energy levels, very good. The number of protons is increasing, which causes the effective nuclear charge to also increase. Okay, very good. Okay. Last slide. This is super quick. You know that, you know that. Make sure you're comfortable with your family group names, which you are. This is super fast, guys. Give me some rapid fire. Give me some characteristics of metals. Go. Shiny. You know what? Let's use a fancier word. They're lustrous. Okay. But they're shiny. What else?
Good conductors.
Good conductors of what?
Heat or electricity.
Heat and electricity. What else? Malleable. Ductile. How about melting points? High, low, relatively high. Okay. How about characteristics of nonmetals? Brittle. Dull. Non-conductive, which if you're a poor conductor, you must be a good insulator. Very good. Okay. Relatively low melting and boiling points. Okay, very good. We're done.